Hi everyone. In this video we are going to talk about lesson 10 of the Particles and Energy Scheme of Work, which is about temperature scales. And it's a bit of an unusual lesson that isn't always taught at Key Stage 3, even at Key Stage 4, in that it introduces the Kelvin scale and this idea of an absolute scale of temperature. And you may think, well, is it really worthwhile to do this? But I think it's really important to really understand the concept of temperature, that we can see it in absolute terms. And what I mean by that is that there is a minimum temperature, there is a lowest possible temperature, and I think understanding that is really helpful to students, because it really brings home that idea that temperature is related to the kinetic energy of the particles. So the way I introduce this is by drawing some diagrams, and as you have seen, if you've been watching the previous videos in this scheme of work, I always start with something quite concrete. So I'm going to start with my ice cube like this. So I'm going to tell students I've got an ice cube that's at -1 degrees C, really close to the melting point of water, which hopefully after the previous lesson they should be familiar with what the melting point is 0. So what I'm going to do is zoom in on the particles in my ice cube like this, as I like to do, and I'm always reinforcing that message that science is about understanding the things that we can see in terms of the things that we can't see. And I'm going to show my particles here like this. This is not the neatest diagram, but it will do the job. Oh, I've done some overlaps, so I would definitely lose marks on my GCSE, but never mind for the sake of today. So I've got my fixed lattice here, but what I really want to emphasize to students is if I'm close to the melting point of water, then my particles at this point must be jiggling so much that they're about to break free from the lattice. So I'm going to put loads and loads of these little curved lines here to show that there's an awful lot of jiggling going on, an awful lot of vibrating on the spot going on. By the way, I use the word jiggling quite a lot, only because Richard Feynman uses it in his lectures. And I'm thinking, well, if it's good enough for Richard Feynman, it's good enough for me. So, lots and lots of jiggling. And I might put something along the lines of a note here that we've got relatively high kinetic energy. And I'll just put Ke for now. You might want to write it out in full. So this is the picture of the particles in an ice cube at -1 degrees C. Now I'm next going to ask students to imagine that I take my same ice cube and I put it in a really powerful freezer, and I take it down to -100 degrees C. And I asked them to think, okay, if I were to zoom in on the particles on this ice cube that's now been super cooled, actually maybe I shouldn't use the word super cooled, I think that has a special meaning, but cooled a lot down to -100 degrees C, well, what would my particles look like? So hopefully they'd realize that if you've cooled it, then you're not going to change the arrangement. They're still going to be in this fixed lattice regular arrangement. But what, if they understand the concept of temperature, what you would hope they would appreciate is that where these particles were jiggling absolutely loads, these particles are going to be vibrating quite a bit less. So I'm going to just draw kind of one line like this. They're not jiggling very much. And I really want to use this lesson to continue to embed that link between the temperature of a substance and the average kinetic energy of its particles. So what I'm going to write here is, well, now we're at a lower temperature, we've gone down to -100, we've put it in this special freezer, we've got a lower kinetic energy on average in amongst the particles. So what I want them to do then is say, well, okay, let's imagine I have these absolutely amazing freezers these are the most powerful freezers that you can possibly imagine. And I take my ice cube and I just keep cooling it, and I keep cooling it, and I keep cooling it. And I'm going to ask that lovely question that we saw right in the very first lesson in this scheme, which is all about the deductions we make from our guesses. And in this case, the deduction we can make from our guess that all matter is made of tiny particles. I want to say, well, okay, if you were to keep cooling this and keep cooling it and keep cooling it, what would you expect to happen? What would you expect to see in your particle diagram? And this is a really good chance to get students thinking about the concept. Because hopefully what they'll recognise is, if you were to cool this ice cube enough, then you would reach a temperature at which the kinetic energy got lower and lower and lower and lower until those particles had 0 kinetic energy. Now I really like doing this one because I start by always starting with the temperature, something that they're familiar with, and then moving this way into looking at the particles. But in this one, I then say, well, okay, let's do our thought experiment now. You keep cooling it, you keep cooling it, you keep cooling it. You would expect to reach a temperature at which you get 0 kinetic energy. And what I do this time, instead of moving this way, I move back that way and say, well, actually, there is a temperature. Scientists have discovered that there is a temperature at which the particles have 0 kinetic energy, and that temperature is minus 273 degrees C. And at this point, I want to tell students that we call that temperature absolute 0. And that is the temperature at which particles in a substance have 0 kinetic energy. So I'm going to put that as equal to minus 273 degrees C. Now, I can then tell them about Lord Kelvin, and you can go into all sorts of detail if you want. But I effectively want to say there is another temperature scale which we've not seen before. We've looked at everything in terms of Celsius, which is the most commonly used temperature scale in Europe, and it's really handy because it has the it's based around water and its melting and boiling point. Now what I want to say is Lord Kelvin came up with a temperature scale that had the same increments, so 1 Kelvin was equal to 1 degree C, but what it did was it started not at the melting point of water, it started at this temperature, which is the lowest temperature anything can be at, the temperature at which particles in a substance have 0 kinetic energy. So I'm going to put that is equal to 0 Kelvin. And as you can see, I'm not just teaching this so that I can get them to do some sums and you know, convert temperatures just for the sake of it. The reason I think it's important to introduce this, even in year 7, is because it's a really nice illustration of that underlying concept that we want to get across, which is the relationship between the temperature of a substance and the kinetic energy of its particles. So then in the second part of the lesson, it's a kind of I do, we do, you do type thing on converting between temperature scales. So this is where we can return to our number line, and I think it's quite helpful to have 2 number lines side by side here, which I'll just sketch over here. So if we put a number line here like this, that can be for the Celsius scale, and then a number line here like this, that can be for the Kelvin scale. So I'm going to add some arrows here like that. Let's get those vertical on the screen. So I might put temperature in degrees C up here, and temperature in Kelvin up here. And what I want to stress to students is that these points come, I want to put them side by side, so like that. So this is going to be minus 273, and this is going to be 0 for Kelvin. Let me move that so you guys can see a bit more clearly. So then I'm going to put the melting point of water, and the way I'm going to show this is to say, where are we? So the melting point of water I know is 0 degrees C. So what would that be in Kelvin? Well, what I would have to do there to get from minus 273 to 0, I'm going to show students, well, you're going to need to go up by plus 273. Well, as we said before, Kelvin ingeniously designed his scale so that it had the same increments as the Celsius scale. So in this case, you're also going to have to go up by 273 Kelvin. And therefore, the melting point of water, when measured on the Kelvin scale, is just 273 plus 273. So then we could repeat this exercise and say, well, we know that the boiling point of water is 100 degrees C. So I could put that up here. That's 100 degrees C. Well, how am I going to work out what that is in Kelvin? Well, I know from here, from the melting point, I've had to go up by plus 100, and I know the increments are the same. So in this case, I've got to draw my line over here. Let's add that on. I'm just going to have to do exactly the same, which is go up by plus 100. So I get plus 273 plus 100, I get plus 373. And you don't need to do the plus there, but students might find that helpful. And then there's some more examples that you'll see in the slides. So one example we've got is how would you write 3 Kelvin in degrees C? Well, I can say if I am doing 3 Kelvin, I've gone from 0 and I've gone up here by plus 3. So that's going to be my 3 Kelvin. So what I'm going to have to do from here, well, I'm going to have to go from minus 273 and then up by plus 3. And hopefully they could work out, therefore, that 3 Kelvin, which is 3 above 0 Kelvin, like this. So let's put 3 up there, is just going to be minus 273 plus 3, which is going to be, where shall I write this? Let's write it up here, minus 270 degrees C. So that's a really nice simple way of modelling how to do those conversions, and you can do them either way, either starting on that side or starting on that side. There's lots and lots of examples that you'll see in the slide. Get students doing lots on whiteboards, get them to lay it out in the way that you want it laid out, like this, so that they're really thinking methodically about it. And as I said before, it's not just about doing the conversions, that's very useful, but really I think the main reason for introducing this topic into year 7 is to really embed that link between temperature and the average kinetic energy of particles. That is the final lesson in that kind of short sequence on temperature. In the next few lessons, we're going to be looking at heat transfer, heating and cooling, and how thermal energy is transferred from one substance to another. Thank you.